Welcome back. So we're going to talk about reductions that will lead to alcohols. And we're going to start by talking about reductions with hydrides. Here I'm going to show you first a flow chart of where we're going to start, where we're going to end ultimately. And what you can see right here is that the ultimate source, if you will, for the reductions could be the carboxylic acid, the ester, or something known as the acyl chloride, which can be thought of a carboxylic acid where the OH has been substituted with a chlorine atom. These particular substances have a pretty oxidized carbon already bound in the structure. We're talking about a carbon with a 3+ state. So we can undergo reductions down to the aldehyde or the ketone stage, in which case the oxidation of the carbon down here has a 2+ charge for the ketone or a +1 charge for the aldehyde. And we could actually carry this even further as far as a reduction is concerned, because we could take the ketone and reduce it all the way to secondary alcohol, which has a charge of 0 on carbon, and the carbon over here will be +1 for a tertiary alcohol. On the opposite end of the spectrum, if we reduce the aldehyde even further, then we can get to a primary alcohol with a oxidation state of carbon of -1, or a secondary alcohol with a oxidation state of 0 for carbon. So what I'm going to show you right now is the reagents that we typically use to carry out reductions in which hydrides H- is delivered into the particular molecules. Alright, so one of the most common ones is known as LiAlH, which is lithium aluminum hydride, represented here in the as a product in this particular reaction. Technically speaking, you make it by reacting lithium hydride with aluminate, and then this produces your lithium aluminum hydride. And I guess this is kind of good that for once we get to talk a little bit about aluminum, since technically I'm the aluminum chemist. But anyway, this is what we consider a strong reducing agent. And notice that I'm highlighting that particular bond in red and differentiating it from the other three, because only one out of these aluminum hydrogen bonds is hydridic, meaning that you have more of an ionic character associated with it. The other three are a bit more covalent, if you will. Not to say that they're not reactive, but not as reactive as this fourth hydride present on the complex. Now, another useful reagent is sodium borohydride, which can be made exactly in the same fashion. Treat sodium hydride with borane, and this yields sodium borohydride. Now, this is a mild reducing agent, and the reason why is because if you look at the electronegativity differences of hydrogen and the central element, for lithium aluminum hydride we're looking at an electronegativity difference of 0.59, whereas for borohydride we're looking at an electronegativity difference of 0.16. So what this is telling us is that the bond in lithium aluminum hydride is more ionic than that in borohydride, which itself can be considered more covalent than the aluminum hydride. And because you have more greater covalent character on this bond, it's not as easily broken, and that's what makes this reagent be mild in comparison to lithium aluminum hydride. Okay, now what does that really imply in terms of the reductions? Well, technically this mild reagent, sodium borohydride, is only going to be useful if we're trying to reduce the partly reduced species. So if we reduce the ketone down to a secondary alcohol, we can use sodium borohydride to make that happen. Or if we have the aldehyde and we want to reduce it to the primary alcohol, we can use sodium borohydride to make that happen. But notice that you cannot really start with the carboxylic acid, the ester, or the acyl chloride to carry this transformation. So you need to kind of be already kind of part of the way into the reduction sequence to be able to use this particular reagent. On the other hand, lithium aluminum hydride is able to reduce all of the different species to the final reduced sequence. So you could start with the carboxylic acid or the ester and reduce it all the way down to the secondary alcohol. You could start with a ketone and reduce that also to the secondary alcohol. And likewise here, you could take the carboxylic acid, ester, acyl, chloride to the primary alcohol. And as I'll show you with a specific version, a different version of aluminum hydride, we could actually stop at the aldehyde stage. But with lithium aluminum hydride itself, this is actually not something that can be done necessarily. So typically we'll just take this all the way to the primary alcohol stage if we start with those things. Now the other thing too that I should mention right here is that even though I'm showing the ketone as being the species that you can also reduce, that's definitely true. But the thing that's not true is that you will be able to reduce the carboxylic acid to the ketone using this type of reagent. That is not really something that's going to happen. But if you do start with a ketone, you can reduce that to the secondary alcohol. And by the same logic, if you do start with an aldehyde, you can reduce the aldehyde to the alcohol counterpart. So these are the things to keep in mind. But technically the end result is the alcohol. You go straight to the alcohol when you use the strong reagent. Okay, now speaking of the variations, there are ways of kind of stopping midway through the reduction sequence. And really what we're making use of here is groups like T-butoxide that are actually rather bulky, right? We're talking about something that looks roughly like shown in this diagram. And putting 3 of those T-butoxide groups around aluminum takes up quite a bit of room around aluminum. So this aluminum hydride bond, it's relatively sterically encumbered, very much difficult to access. And by the same logic, the aluminum hydride bond is not really all that easily accessible, and it really can attack any type of substrate. That's going to be something difficult for it to do. So we're going to kind of bank on that type of problem that bond is having to deal with, having those T-butoxides. And another one that also kind of goes along those lines, but it's not as bulky, is the diisobutyl aluminum um, complex. In fact, if we start first with triisobutyl aluminum, then upon heating we can actually undergo a decomposition that produces isoprene, but also produces this material right here known as DIBAL for diisobutyl aluminum. And some people even write DIBALH to represent that you have the hydrogens in there. We're gonna basically see how those variations of lithium aluminum hydride can be used to kind of stop somewhere midway. So we could maybe stop at the aldehyde stage if we use some of those bulkier materials. But like I mentioned earlier, if you start with a ketone, you will go to the secondary alcohol using LiAlH. Starting with the carboxylic acid, you will go all the way to the primary alcohol. Starting with the aldehyde, you will also stop at the primary alcohol. So these are the sequences that we're going to study. Now in the next video, I'm going to show you specifically how we carry out these particular reductions to make primary alcohols, to make secondary alcohols, and also to prepare aldehydes themselves. So I'll see you in the next video.